All right, the practice example will be draw a voltaic cell. So we'll do that. The voltaic cell is going to consist of an anode and a cathode. Let's go ahead and draw a beaker for the anode and one for the cathode. The anode. All right, in which silver ion is displaced from solution by aluminum metal. Now this terminology, silver ion is displaced, that comes from single replacement reactions, about which ones. But if you think about silver ions reacting with aluminum metal, what's going to happen if you take silver and aluminum? There's going to be a redox reaction. Okay. And so silver ions plus aluminum metal yields what?
Wait, wouldn't it be 3 silver? I mean, yeah, 3 silver?
Yeah, it'd be 3 silvers. There are different ways you could do this. You could get it in a single replacement form, or you could just do it like we did at the beginning of the semester, you know, the general redox method. This is going to produce
Aluminum 3 plus.
So we're skipping the general redox and just figuring it out. So, and silver metal. And so we call silver ions the oxidizer or the reducer? Oxidizer. Aluminum, the reducer. And so the oxidizer pulls the electrons in. So we're pulling the electrons in. What's pulling the electrons into the cathode? The oxidizer. And so we need our oxidizer over here to pull in the electrons. We need the reducer over here to supply the electrons. So what's the reducer going to be? A little chunk of aluminum. We'll just stick a chunk of aluminum in the anode beaker. Show the direction of flow of electrons. Also indicate the direction of flow of cations and anions from the KNO3 salt bridge. Write an equation for the half reaction occurring at each electrode. Write a balance equation for the overall cell reaction, and write the cell diagram. I'd add one more thing to this, and I'd ask you to tell me the potential, the standard cell potential. But basically, this is like the standard question you have to do. And so this is our cathode compartment, but what is our actual cathode? What should we make our cathode out of?
Silver?
That's probably the best. Why would silver be the best metal to make our cathode out of?
Because you know it won't react with the silver ions?
Yeah, one, it's not going to react with the silver ions. And two, when we form the silver metal in the reaction, it would be nice to put silver on silver. This way, we don't have to scrape off the silver off the electrode to recover it. We could use gold, but we'd put silver coating on gold. Do you want to do that to your gold? Or platinum? Probably not. We could put silver on graphite. It's okay, but when you scrape off the silver off the graphite, you might also get a little bit of graphite in your silver, which isn't so good. And so in this case, probably silver ion. What about using iron? Iron's no good. Why?
Will it precipitate or make a...
Iron will react directly with silver ions. And so we wouldn't use iron. You know, it's not because we're going to coat silver on iron, which we would. It's because the iron would react directly. And so which way are the electrons flowing?
Anode to cathode.
Anode to cathode. So what was the basic question about this, the salt bridge?
The salt bridge was asking. Okay, so for the potassium, apparently the potassium went to the, I think it was the silver, yeah.
The cathode.
Yeah.
Cations go to the cathode.
Oh. Oh.
Potassiums go to there.
Cations go to the cathode.
Cations go to the cathode because the cations are being consumed in this reaction. We get silver ions plus an electron goes to silver solid. Right?
Anions go to anode.
Anodes go to the anode. That's where the name comes from, cathode and anode.
So if we had, that makes sense. So for example, if our salt bridge was like NaOH,
Mm-hmm.
then the Na would go to the cathode and the OH would go to the
Yeah.
That's all.
Okay. All right, and then you'd finish the rest of the problem. All right, other questions? No? Uh-huh.
On the test, are we gonna have? Sorry.
It's okay. It's okay, go ahead.
On the test, are we gonna have the redox?
Chart? Yes, you're going to have the redox chart on the test. Okay, number 14 on the correct. All right, number 14 asks what? Well, we have this cell. What's the anode in this cell? Aluminum. What's a cathode?
Hydrogen.
Well, it's a hydrogen, the SHE, using a platinum as the actual electrode. Platinum electrode in the hydrogen cell. So which species is pulling the electrons through the external circuit?
Hydrogen. Plus. Platinum.
Platinum isn't pulling, it's just the H plus. So the answer would be F. Yeah, that's true. I don't know. I guess I had extra room, so I thought I'd add more. All right, other questions?
16.
16, okay. Doubling the reaction doubles. Doubling the reaction doubles E of the cell?
No.
No.
No. Doubling the reaction would double the life of the battery. You know, you have twice as much. It's just a bigger battery, but it doesn't change the voltage, because there's only one thing that's going to change the voltage, and that would be the well, the concentration. Yeah, delta G is going to have an impact. The concentration or the pressure. Temperature will too. B, E naught of the cell. Doubling the reaction, would it double the standard cell voltage?
No.
No? Okay, good. Well, I guess I don't really have to explain those now. So no, no.
No. It's not only in the
This goes no, no. Yes, 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 yes. So there's a lot of circling. So why doubling the reaction here? If you double the life of the battery, do you get the exact same amount of energy if you double the life of the battery, or you you just doubled the energy, right? And so delta G's energy, you didn't double the driving force, right? If you doubled, like I have, rather than I'm using 1 pound of aluminum, I'm going to use 2 pounds of aluminum. If you use 2 pounds of aluminum here, did you just double the driving force?
Wait,
Wait a minute.
just for aluminum though?
Just aluminum?
Just aluminum?
Just aluminum.
You doubled just aluminum.
Yeah, okay, let's go from 1 pound of aluminum to 2 pounds of aluminum. I'm going to get twice the voltage.
Voltage didn't change.
If it's more surface area.
The voltage didn't change. Well, surface area we're going to ignore. The voltage, if it's the if the anyway, a similar analogy would be like this. If I pour you a glass of lemonade, it's pretty sweet, right? If I pour you twice the 2 glasses of lemonade, it's twice as sweet. 2 glasses of lemonade should be twice as sweet as 1 glass of lemonade. True?
False.
False. And so it's the same thing here. You know, it's not going to change it, right? What would change it is by changing the concentration. Rather than, if let's say I'm mixing the lemonade and I use half as much water, make it twice as concentrated. If I make it twice as concentrated, then it should be twice as sweet, right? That's going to change. And so here, did you have to precisely measure this? Because if you accidentally added a milliliter or 2 milliliters or 3 milliliters too much of this solution, do you watch the voltage pop up each time you add? No. It's going to have a certain activity, and that activity is going to be defined as, now let's look at it under standard conditions. If you look at it under standard conditions, you have 1 molar silver ion. Let's say I have a gallon. 1 gallon of 1 molar silver ion versus 2 gallons of 1 molar silver ion. Which one's more concentrated? 2 gallons of silver ion. Is it more concentrated than 1 gallon of silver ion? No, it's the same concentration. So what's the difference? The difference is you have twice as much quantity, which means it should last twice as long. And so when we're looking at cell voltage, we're looking at, you know, the pulling power of this. You know, times oxide and gold. And to make this pull more, what we would do is we would, because there's a tug of war, right? We would have to increase the concentration. If we raise the concentration of which aluminum?
Aluminum ion.
Over here? Yeah, then that's going to change the potential, for sure. Delta G's driving force, but a little different because delta G is the energy that we're going to get from this, right? The thing about E is E's kind of normalized. When we look at E, you know, there's that per mole thing. The voltage, it's volts per mole. Remember that in the Nernst equation? So somewhat normalized. You could have 50 moles of electrons, but you know the voltage you'd have to divide by 50 versus 10 moles of electron. Voltage you divide by 10. And so these are extensive. Energies are all extensive. It doesn't matter what conditions you do it under. Like for example, you know, standard conditions 1 bar. If you did it at half a bar, let's say I did this reaction at half a bar and then I just doubled the amounts. What do you expect to happen to the energy? As long as you keep the conditions the same, the energy content should double. And so that's why all these just doubled, but the electrical potential, the voltage didn't. Is that clear enough for this one? Okay, other questions? No? Okay. You can't, there's certain things you can't do. You can't do this without the, like number 18, you can't do that without the chart. There are two 18s. This second 18 is supposed to be 19. All right. If there are no questions, then we're going to move on.
Did you say you were going to give back our formal labs and our chapter 19 test tomorrow?
Well, I said yes. I'll give you a chapter 19 test. Which would you rather have, your formal lab or your chapter 19 test? Chapter test. I'll give you both, obviously. But you got the rough draft back, so you kind of know what you're supposed to write for your formal report.
I just want to know our grades.
Yeah.
That we got.
Right. Chapter 19 you'll get back. The formal lab I'll have done. I've already graded a bunch of them.
Chapter 19 and the lab tomorrow, you said?
No. Chapter 19 for sure. With the lab, the formal lab write-up, I might need more time.
How are the labs looking so far? Good grades? A's?
Lots of A's, right?
There are a number of A's, yeah, so far.
Great.
Number.
Like one in a yellow folder by chance.
You'll see when you get it back.
35. He specifically remembers one of the yellow folder was terrible.
No, I don't. All right, chapter 25, this is the last chapter we're going to cover, nuclear chem. This stuff is different than everything we've been talking about, because everything we've been talking about has been chemistry. So what is the difference between chemistry and nuclear chemistry? So, does somebody know?
The energy.
One is the energy. In nuclear chemistry, the energies are they're inside the nucleus. They're huge, huge compared to chemistry. Chemistry, the energies are small. Why is there such a big difference? Because in chemistry, you would think that the energies can be huge too. You look at those very violent redox reactions that might occur. Those energies seem large, but those energies are actually still relatively small in comparison to nuclear chem. And so nuclear chemists look at different things than chemists do. For chemists, chemists are most interested in what type of interaction? Electrical interaction. So chemists are most interested in positive and negative interactions. This is why quantum chemistry is so important, because quantum chemistry shows you how what is distributed in the molecule. The charge, right? The electron density. Shows you how the electron density is distributed in the molecule via orbitals, right? And looking at the interactions between positive and negative is very important. And not only that, you have to look at how these orbitals interact with one another, forming bonds and that kind of stuff. Nuclear chemists, they don't really care about the electrons. And we don't use quantum chemistry for nuclear chemistry. Do you know what nuclear chemists are most interested in? They aren't most interested in electrical interactions, because electrical interactions are insignificant compared to This goes back to chapter 2. In chapter 2, do you recall how the masses of isotopes are determined? Protons, neutrons, and electrons. And so let's say I want the mass of the fluorine-19 isotope. An atom of a specific isotope is called a nuclide. So an atom of so I'm interested in fluorine-19. How much does a fluorine-19 atom weigh? 19 AMU? You should say roughly 19 AMU. It doesn't weigh exactly 19 AMU, does it? Because this is called the mass number because it's close to the mass, but it's not the actual mass. It's close to the mass. Why is the mass number close to the actual mass of the isotope? Yeah, because electron masses aren't that significant. A proton weighs proton weighs 1 U. A neutron weighs 1 U. We got 9 protons, 10 neutrons, so it's going to weigh about 19 U. You guys remember Z, right? And what do we call the mass number? A. Z and A. But 19U isn't precise enough. I want something a little more accurate, a little bit more precise. And so how can I determine what the mass of fluorine-19 is? Well, did you guys do this in Chem 1A? I know the composition of this because I know A and Z. So if you know the composition of this, you have 9 protons. And do you know how much a proton weighs? No, but you can find it in our book, right? In chapter 2, there's a table telling us how much a proton weighs. Yeah, so we just do 9 times the mass of a proton, right? And then how many neutrons? 10 neutrons. We do 10 times the mass of a neutron. And how many electrons? 9 electrons, so 9 times the mass of an electron. And we should sum that up, and we should get a, yeah. We sum up the masses, we should get the mass of a fluorine-19 atom, or nuclide, or an isotope. Did you do that in Chem 1A? You might have done this in Chem 1A, but there's but let me ask you, is this true or false? True or false? That is, the sum of the masses is equal to the mass. True or false?
False.
Probably false. It's too easy.
Probably false because it's too easy.
Well, false because you don't really like find the masses by the average of it, so it just stays.
We find that, well, I'm just talking about one isotope. Then we figure out how many naturally occurring isotopes there are, and then we determine the mass based on that.
I'm going with true. Someone else is going with false.
You're going with true?
Yeah.
It could be neither because it could be like a very good estimate.
No, the answer is it is false. So why is it false? Maybe it's too easy. It just seems so obvious, and if it's such an easy calculation, why weren't you doing it in Chem 4? You might have remembered doing a calculation like this. You might have done a calculation like this to calculate something. called the mass defect. Have you heard of the mass defect? Mass defect is briefly, it's talked about in chapter 2 in the homework. I usually assign this as a homework problem. You know, calculate the mass of the fluorine-19 and compare it to the actual mass. The actual mass is less. You know that? And so it actually turns out that this is greater than the actual mass of the fluorine-19 atom. It's greater than. And so the sum of mass is greater than. Well, what happened? What happened was some mass disappeared. Remember in Chem, in chapter 1, they talked about the conservation of matter, conservation of mass? Well, here, mass wasn't conserved. What happened to the mass?
It's transferred into energy.
Yes, right. It was transferred into energy, and we call that energy. Some mass was lost. And converted into the what we call the nuclear binding energy. Why do we need the nuclear binding energy?
It's hard to say again.
Yes. You have 9 protons in a tiny nucleus. 9 protons. What holds these together?
I was told that neutrons have something.
Yeah. So neutrons might be the glue that holds the protons together, right?
Yeah.
But well, we're going to say what holds these together? What holds these together is the, at least in terms of energy, it's the nuclear binding energy. This is why electrical forces aren't so significant to nuclear chemists, because if you think about the electrical repulsions, you know, you have 9 positive charges crammed into a tiny volume. Why don't they repel each other and scatter in opposite directions? Why do they stick together? And so there must be something stronger than electrical forces that are doing it, because for us chemists only care about electrical forces, you know, like redox or whatever else, positive, negative, bonding, this kind of stuff. But nuclear chemists, electrical forces aren't so significant, you know, to nuclear chemists, because they're dealing with much larger energies, like this. All right, so the nuclear binding energy must be very strong, right, to hold the nucleus together. And so do you think every nucleus of every element, of every isotope, of every atom is the same, has the same binding energy? No. The binding energy varies. You know, there's some nuclei that are very strongly bound, which would have a very high binding energy. There's some nuclei that have very weak binding energies. The ones with very weak binding energies have unstable nuclei, right? An unstable nucleus is going to do what? Well, it can't stay unstable forever, right? It's high energy, unstable. Eventually it's going to drop down in energy and become something more stable. And so in that process, it'll decay. And so well, let me back up one step, because I think this is maybe a good time to review. And so if you can't just add up the pieces, how are the masses determined for specific atoms, isotopes, nucleids. If you can't just add it up, and the thing is, you can't just say, okay, 10% of the mass is going to be converted, right? Because is that a fixed number? Is it always 10% of the mass is converted? No, because some nuclei are strongly bound, so maybe more mass is converted. Some nuclei are more weakly bound, so maybe less mass is converted. And so it's not fixed. And so if it's not fixed, how do you determine the mass of a atom? Can you weigh a single atom on the balance? No. You can weigh a mole of atoms, right? But can you imagine getting it isotopically pure? Are there tweezers small enough that you can pluck out the hydrogen 1 from the hydrogen 2?
Are there?
No. Actually, there's ways of doing it. Not using tweezers, but by using magnetic fields. Which brings us to, how do you weigh atoms? Because where did this actual mass come from? Actually, you know what the actual mass of fluorine-19 is? There's only one naturally occurring isotope. The actual mass of fluorine-19 is 18.998403. If you add up all the protons, neutrons, and electrons, you get over 19 U. And so the masses don't match. So how are individual atoms weighed? Using an instrument that was introduced in chapter 2. Instrument was called a...
What's the first letter?
M.
M.
A. S. S. Massometer. Massometer sounds too cartoonish, so nobody would take it. No. But mass spectrometer, right? That's it. Yeah, with a mass spectrometer, you can weigh it. Say you weigh these fluorine-19, you can figure out what the mass is, and then you see what we call the mass defect is, right? And we could determine the stability, the relative stability of the nucleus, right? When we're looking at the stability, how does one determine how stable it is? Because what we're doing is, in nuclear reactions, we're going from less stable nuclei to more stable nuclei. In chemical reactions, we're typically going from less stable bonds to more stable bonds, right? And so a lot of parallels in certain ways. But the thing is, we know what makes a good, strong bond, right? Using valence bond theory, using MO theory, using lattice energies, that type of stuff. We know what makes a good, strong bond. But what makes a good, strong nucleus? What makes a good, strong bond, we look at certain things, orbital overlap, single bond, triple bond, this kind of stuff, right? But when we think about what makes a good, strong nucleus, you tell me what makes a good, strong nucleus. Why do some nuclei have a greater stability than other nuclei?
Smaller, more size.
Size, maybe, yeah. Size, yeah, that could be one critical factor because for sure, if something is radioactive, you know what a radioactive isotope is? It decays, yeah. Radioactive isotopes have unstable nuclei, and so they undergo decay, which means they break down into other things that are more stable. And so if we just look at the periodic table, we can see certain things that are very radioactive. We go lead. Is lead radioactive? In general? No. Bismuth? Bismuth radioactive?
No.
No. Polonium. Polonium radioactive? Sounds like it. For sure it sounds like it. And polonium might ring a bell because I was watching I haven't finished I was watching a documentary on Netflix about this ex-Russian spy who consumed polonium-laced tea. Have you heard of that? Died a miserable death, actually, from polonium injection. And then the same thing happened. There were two journalists in Los Angeles who were poisoned by polonium somehow and died miserable deaths too. That just happened like recently, 5 years ago or something like that. Did you hear about them? Yeah. Well, anyway, polonium is, yes, radioactive. So maybe it is. You know, the bigger, because from 84 on, like AT, actinium, radon, Rn, francium, radium, those are all radioactive. And so maybe having a big one makes it radioactive. But that's not true, because there are small atoms, small nuclei that are radioactive too. Can you name one? Carbon-14. Carbon-14 is radioactive. It's small. So what makes that radioactive? Well, you're good. And so with this nuclear chem stuff, that's good. So how does one determine? Well, we're going to look. Are we going to come up? This is just a general question. If we're interested in nuclear stability, you know, we want to figure out what makes something radioactive versus something that's not radioactive. What do you do in the scientific method? What is the scientific method to you? And so what I often hear is this: we need to form a hypothesis or something and then test it. So give me a hypothesis and let's test it.
Like, that's not how it works, you said last time.
Well, I'm saying, you know, I seem to see an overemphasis of this when, you know, a hypothesis, you're going to have to know a lot. I mean, if you're going to come up with some kind of hypothesis,
You should have the observation
huh?
first.
Yeah, we're skipping a big part of this. You know, it's not supposed to be this complicated, because how, you know, to me, if someone were to ask, okay, let's use a scientific method to figure out why certain things are radioactive and other things aren't. And if somebody came up to me and said, oh, you have to form a hypothesis and then test it, I'd be blown away, because that would be way too hard. You know, science, is it supposed to be that hard?
Yes. That's why we get paid more for it.
No, it should be a lot easier than that. Because you know, I would be very curious to see what kind of hypothesis people come up with for this. You know, but do you think it's going to be a very sound hypothesis? No. And so you know, in this case, well, the first question is, well, even if it's radioactive, we know for sure it's unstable, right? But we want to know the degrees. We can't just have, okay, these are all unstable because they're radioactive, these are all stable because they're non-radioactive, right? Because the non-radioactive elements, do you think they're all going to have the same stability in the nucleus? Like for example, carbon-12, you know, carbon-13. Those are two non-radioactive isotopes of carbon. But carbon-12 and carbon-13, exact same stability for the nucleus? No, it just doesn't make sense. So what we want to do is we want to figure out what makes, for example, carbon-12 more or less stable than carbon-13's nucleus, right? And that will give us more insight into what's happening with this. And so first we have to figure out, well, which one is more stable? Is there a way to figure out which one's more stable? And so how does one determine nuclear stability? How does one determine nuclear stability?
Break the nucleus.
Try to break the nucleus? Yeah. When you try to break the nucleus, unfortunately, bad things can happen. Like, yeah, a nuclear explosion.
Right.
Nuclear explosion is much more violent than a chemical one, because much more energy is released.
Look at the half-life. Longer is more stable.
Well, yeah, maybe the half-life, you know, that might be. Those are good. You know, these are all good ideas, but One is, okay, measure the half-life and then see. Another might be to,
But it doesn't go upwards. Vice versa.
I'm sorry?
I said you could put it in like lab rats and see how it affects them.
Okay. Maybe we could think of a more humane way of testing nuclear stability. You know?
Sometimes you have to get your hands a little dirty.
Right.
Gotta make all-
The funny thing about radiation and cancer is this, you know, and I hear this a lot. Oh, you know, that person's totally fine. You know, that person's been exposed to radiation and they never got any cancer, right? It's the same thing. You see people who've been smoking all their lives. They're 90 years old. They die of natural causes other than cancer, right? It's kind of this statistical, you know, coin flip. You know, some people are going to be unlucky in that. And just because somebody was lucky and they made it doesn't mean that everybody's going to be lucky. Right? Well, anyway, how does one determine nuclear stability? An easy way of determining it is by looking at the nuclear binding energy. But the thing is, big nuclei are going to have huge binding energy. Small nuclei will have small binding energy. So what we have to do is we have to level the playing field. Just because it's big doesn't mean it's stable. And so a nuclear binding energy per what we call nucleon. What is a nucleon? A nucleon is either a proton or neutron. So what we're going to do is figure out how much binding energy there is for every proton or for every neutron there is in that nucleus. And the greater the nuclear binding energy per nucleon, the more stable the nucleus should be. Is that right? Yeah, that makes sense. And so how does one determine nuclear stability? Well, maybe this is one way. You know, other way would be, is it radioactive or not radioactive? Its half-life maybe, etc. Could be other ways. This is not necessarily the only way. All right.
Next question, do you have a calculate the nuclear binding energy?
Yes. Now, how do we determine the nuclear binding energy per nucleon? How we determine the nuclear binding energy per nucleon is the nuclear binding energy is called the NBE. And the NBE is determined, you know, by this equation. Delta E is equal to the nuclear binding energy. In this case, when we're looking at delta M C squared. Delta M is what we call the mass defect. So C is the speed of light, which is 2.998 meters per second. And so it's just delta MC squared. And we can calculate it. Now, how do we determine the mass defect? Delta M is equal to the actual mass minus the sum of the masses of the proton, neutron, and electron. And so the actual mass might be 18.9. The sum of the mass is 19 point something, and then the difference would be how much mass was converted into energy. Well, when we do this, typically when we look at the mass of individual atoms, do we use grams, kilograms? What do we use when we're looking at masses of individual atoms? Atomic mass units. And so what we're going to have here is this. The units of nuclear binding energy will be in terms of U, but U, the atomic mass unit, isn't the way we should leave it. What we're going to do is we're going to convert U into kilograms. How do you convert U into grams? Everybody should know this conversion factor. That is, in 1 gram, how many U are there? Do you know how many U are in 1 gram? The reason everybody should know, you should either be able to derive this, you could derive this easily based on the definition of the mole and definition of the U. But there's no point in deriving it because it's so easy to remember. How many U are in a gram? Avogadro's number. 6.022 times 10 to the 23rd U for every gram. Then we can convert that into kilograms. 1,000 grams per kilogram. Grams cancel, U's cancel, and that gives us kilograms. So the mass defect in kilograms. And then C squared will give us units of meters squared per second squared. So the units are going to be kilograms, meters squared per second squared. What is a kilogram meter squared per second squared? A joule, right? That's the definition of a joule. It's defined as a joule. And so we can figure out the joules of nuclear or kilojoules of nuclear binding energy per nucleon. It's actually going to be in joules, and it's going to be a very small number. Even though it's a small number, we're talking about per nucleon, which is very small. And so here we can get that. And so we can get some kind of idea about the stability of the nucleus, right? By weighing the atoms. How do we weigh the atoms again? We can use like a mass spectrometer. And then summing up the masses. This is just in chapter 2. And so in chapter 2, I usually assign a homework problem. It's calculating the mass defect in fluorine 19. If you want to see mass defect problems. Okay, so we're going to see a range of stabilities, right? A range. And then some of these nuclei are going to be terribly unstable. And we call those nuclei or atoms radioactive. Radioactive isotopes. An atom of specific isotope is called a nuclide. Atom. Radioactive isotopes have highly unstable nuclei. They're going to react or decompose, decay. So if we look at a radioactive atom here, this nucleus is unstable for some reason or the other. We've got to figure out the reasons for instability, right? And so we've got an unstable nucleus. It's going to go decay. When it undergoes decay, it forms more stable nuclei. And so we're going from, high energy, less stable to more stable. Not necessarily completely stable. I mean, we could go from one radioactive one to another radioactive one. But anyway, this decay process is going to emit what? Emit radiation. And so radioactive isotopes emit radiation and undergoing decay to things that are more stable. Again, more stable doesn't mean stable. It's more stable than what we started with. And so let's take a look at radiation. first. Radiation was discussed in chapter 2. And so we'll do a quick review of radiation. It's also discussed in this chapter as well. And I'm not going to go in order, this chapter, just to make things quicker. I'm going to go out of order. Okay. And so when we're thinking about radiation, we have two types of radiation. We have particle radiation, and we have electromagnetic radiation. And so can you tell me the types of particle radiation we encounter? Okay, well, gamma is in this category over here. Gamma is electromagnetic, high energy light, is what we call it. For particle radiation consists of actual particles. Lights consist of photons. Photons don't have any rest mass, and so we don't consider those particles. We just consider those energy packets. Waves. And so an actual particle being emitted, well, we're thinking about this. Well, this nucleus is unstable, right? So maybe it doesn't have enough binding energy, so maybe part of it breaks off. And so let's say two protons and two neutrons break off the nucleus, What are two protons and two neutrons called? Well, two protons is Z is equal to 2. Z equals 2 is helium. And so if two protons, two neutrons break off, we call them alpha particle. Alpha particles are the nucleus of a helium atom. And we'll just pick the helium-4 as an isotope. And there are no electrons here, right? Just a chunk of the nucleus broke off. It's emitted as an alpha particle. Are alpha particles radioactive? Does helium have an unstable nucleus or a stable nucleus? What do you think? It's stable. And so helium itself is not radioactive. If you got hit by alpha particles, would that make you become radioactive? Would you start to glow with radiation or something like that? Or what would happen? If you got hit with alpha particles, well, it depends on how many alpha particles you get hit with, because it could be a very miserable death. Polonium is an alpha particle emitter. And so these people, this person consumed polonium tea or whatever, tea spiked with polonium, and you think, okay, all you have to do is get rid of the polonium out of your body. But is that something so easy to do? No, polonium's a kind of a heavy metal. One way you might try to get rid of the polonium is to use what? Maybe use a chelating agent like, what would be a chelating agent that you might use to try to get rid of polonium? Starts with an E, ends with an A. EDTA. So I think the person underwent chelation therapy in the hospital, right? But I don't think it was successful. I think it removed some, but not enough. And it's unfortunately, it's a very slow and painful death that they have. Because the polonium is an alpha emitter, and alpha particles cause what kind of damage? So if you were hit by alpha particles, well, alpha particles aren't radioactive. The damage they cause is chemical. Why would alpha particles cause considerable chemical damage? Yes, they're strong oxidizers, incredibly strong oxidizers. Strong oxidizers have very, very high oxidation potentials, or strong oxidizers have very, very high reduction potentials. Very high reduction. What's the very highest reduction potential you know? The highest reduction potential you probably know is fluorine with a potential of, is it 287 or 3? No, fluorine, okay, positive 287 volts. So around positive 3 volts. Where would alpha particles be? Greater than 3 volts? Less than 3 volts? About equal to 3 volts?
Off the charts.
Off the charts. Off the charts high, right? This is way beyond 3 volts here, right? In terms of potential, way beyond. And so this is going to cause a lot of chemical damage, right? The reason it's radiation is it was spit out by an unstable nucleus, like polonium. And the alpha particles, let's talk about radiation damage in a minute. So alpha particles are called ionizing radiation. Why? Because they have an extremely high reduction potential, which means they powerful oxidizers, which means they want what? What do alpha particles want the most? Electrons. And so these are going to oxidize things. The danger with alpha particles is they're gas. And so if you inhale alpha particles, they're going to take electrons from your lungs, right? Whatever tissue they come in contact with. Alpha particles are less dangerous if you get skin exposure, because skin is subjected to all kinds of radiation. You walk outside, you get bombarded with radiation, right? Cosmic rays, whatever else. Well, cosmic rays are more penetrating, UV radiation, etc. And so when I was taking biochemistry, I learned that, and this is a number that stuck, but I took biochemistry so many years ago that the number has surely changed, but I still remember this number. And the number was that every day your DNA gets cleaved, that is, the bonds in DNA get broken at least 200 times per day. And so if you're thinking your DNA is being cleaved 200 times a day, that's going to cause a lot of defects, which is, in other words, mutations, right? But why doesn't it cause a huge number of mutations? Well, in biochemistry, you learn about repair enzymes. So these repair enzymes go in and repair the damage that was caused by radiation exposure. And so even though your skin, DNA is being cleaved all the time, it doesn't result in a huge number of mutations. How about your lungs? Do you think your lungs have repair enzymes to fix the damage, or internal tissue? Does your internal tissue have repair enzymes to fix DNA cleavage?
Mm-hmm.
Do they?
I think it does when they're during the replication, right? They check it.
All right. Do you think well, let's ignore that question then. Let's just put it. Do you think your lung tissue is as effective at repairing damage as skin? No. And so what happens is this causes a lot of damage, this ionizing radiation, especially inhaling it or ingesting. If you ingest polonium, you're going to have a constant source of alpha particles. And how do you get rid of the polonium? Well, you could try chelation therapy, you could try other things, but it's not so easy. And so once they were poisoned, there was nothing they could do, unfortunately. And so it's pretty sad reading these things. And also watching it was pretty depressing. I haven't finished watching it. It just depends on the mood. So anyway, let's go on. So that's alpha radiation. Well, how bad is alpha radiation? Well, let's talk about radiation exposure, because I used to work with radiation. But I used to work with X radiation. When I worked with X-rays, I had to wear a badge, radiation badge. And the radiation badge, there's a piece of film inside there. And then every month I'd turn in my radiation badge, and then they'd check it. They'd check how much radiation I was exposed to. And if I was exposed to too much radiation for that month, then the next month I wasn't allowed to work with as much radiation. It was like curtail. But I always thought about that. I always thought, gosh, this is kind of ridiculous, because here, you're just working away, and unknowingly you could be being exposed to huge amounts of radiation and won't find out until the next month, right? And so then I was thinking, But what's lucky is that I was only working with one type of radiation, and I knew the source. The source was using X-rays look at crystal structure. And so the source wasn't so good. But what happens just in general, like for example, you know, you might not know what types of radiation you're being exposed to because there are other types of radiation, aren't there? What other types of radiation are there? And so let's take a look. There are beta particles. What are beta rays made up of? Alpha rays are made up of alpha particles. Alpha particles is helium. Beta rays are made up of beta particles, and beta particles are electrons. And so beta electron, that doesn't sound so bad. You know, just build up static electricity or something like that. Get hit with that. But it depends on how fast these electrons are moving. And one thing that's kind of weird is where are these electrons coming from? Usually the electrons are going to come from the valence shell or the core shell. But these electrons are very different. You know, we don't call them electrons, we call them beta. We call them beta because of the origin. You know what the origin of these electrons are? These are electrons that originate from the nucleus. So you ask yourself, how many electrons are there in the nucleus? 0. And so how can we get electrons from the nucleus? These come from a radioactive decay process. In other words, they come from some kind of nuclear reaction that happens within the nucleus. And so we'll just call it decay. There are lots of different radioactive decay processes. Well, some of these radioactive decay processes spit out alpha, some spit out beta. Are there other types of radiation? Well, beta, what do you think about beta? As dangerous as alpha?
No.
Beta is ionizing, but I don't think that this is dangerous as alpha, right? High energy electron might knock another electron off, right? Cause ionization to occur. But you could be deceived because of the shielding. You know what's required to shield you from alpha particles? If you want to protect yourself from alpha radiation, what do you need? You need a lead jacket, you say? No, you don't need a lead jacket. To protect yourself from alpha radiation, all you need is like a sheet of paper, right? A sheet of paper, why? Because alpha particles are so highly reactive, and paper has electrons that alpha particles can oxidize the paper easily, right? And so to protect yourself from alpha radiation, you just need a piece of paper or something simple. Anything. To protect yourself from beta, a piece of paper won't do it. You need something more. What would be good at capturing electrons to protect or shield yourself from beta? Like aluminum foil. So get a sheet of aluminum foil, you can protect yourself from that. How about gold foil? Would gold foil work?
One would be really expensive.
Well, yeah. How about I'm going to use gold foil to protect from alpha particles. You'd think that should work pretty well. It'd be expensive, right? But do you guys remember the Rutherford experiment? The alpha particles just shot through it. So yeah, you got to watch out because maybe it can shoot through it. And so then you might be exposed to alpha radiation. But in theory, you just need a piece of paper, something to react with it. And then once alpha particles take 2 electrons, what does it form? Helium gas, which is pretty inert. All right, what's another type of particle radiation? These two are covered in chapter 2. This one's in chapter 3. Another type of particle radiation are neutrons. You know, sometimes neutrons are spit out from the nucleus. This makes more sense than electrons. You know, but it depends on this decay process. This is why electrons are spit out. But these neutrons can be spit out too. What do you need to protect yourself from neutrons? Yeah, you need something that absorbs neutrons well. What absorbs neutrons well?
Water.
Water can absorb neutrons. Boron atoms, surprisingly, can absorb neutrons pretty well. So we'll talk about these. We could have protons being emitted from the nucleus as well, and etc. There's positrons. You know what a positron is? Positron? Positron is a positive electron. A positive electron is a piece of antimatter. Okay, those are some particle radiation. What about electromagnetic radiation, EM radiation? What types of EM radiation are we going to encounter from radioactive elements? 1, X-rays can be emitted. 2, gamma rays. X-rays and gamma rays. Both of those are ionizing because those photons pack a punch and they can excite electrons off the atom, resulting in ions. So it's ionizing radiation. And so the first thing we're going to do is we're going to look at the effect of radiation on matter, which is at the end, 2510. Here's what a radiation badge looks like here. But a radiation badge, you know, when you're thinking about it, it really depends on the type of radiation you're exposed to, because, you know, as far as electromagnetic radiation, there's more, right? These are ionizing, but there's UV, violet, etc. So let's look at radiation dosage, because what I get back is my dosage of radiation, and I couldn't exceed a certain dosage of radiation. The type of dosage I get back is measured in curies or becquerels, right? And so, you know, over a certain amount of curies or becquerels of radiation per month was too much. And so what is a curie or becquerel of radiation? A curie or becquerel of radiation is you know, 1,000 curies or 1,000 becquerels of radiation would be 1,000 disintegrations, that is 1,000 decays per second. And so that would be like 1,000, you know, like gamma ray photons per second. Okay? Or 1,000, let's say, alpha particles per second. That would be 1,000 curies. Now, well, actually, curies like that. Becquerel, because you know, these numbers are much bigger than 1,000, and so we have this 1 curie is 3.7 times 10 to the 10 becquerels. Becquerel is a disintegration per second, and so it's just these huge numbers. Now. I know what type of radiation I was exposed to. I was exposed to X-rays. But what would you rather be exposed to? Would you rather be exposed to 1,000 curies of X-rays or 1,000 curies of gamma rays?
X-ray.
I'd pick X-rays for sure, because gamma rays would cause a lot more damage, even though they're both 1,000 curies of radiation, right? And so there's that kind of disconnect there, because, you know, or let me put it this way, what would you rather be exposed to? You know, 1,000 curies of gamma rays or 1,000 curies of red photons? You know? Red photons, because 1,000 curies would do a lot less damage of red photons versus gamma ray photons. And so Curie's not the most, unless you're only exposed to one type of radiation. If you're exposed to multiple types of radiation, then you'd want to know what your exposure is, right? You want to know how many Curies of gamma rays versus how many Curies of X-rays you're exposed to, because they're going to have different amounts of energy. They pack a different amount of punch. And so what comes next is a RAD, you know, radiation adjusted dose, or gray. And when we're looking at rads and grays, what we see is this. It's the amount of energy of radiation per kilogram of matter. The amount of energy per kilogram. And so this might be a little bit better, because we're thinking, okay, if your dose was 1,000 rads, that would be 1,000 joules per kilogram of matter worth of radiation. But we run into the same exact problem, right? The same exact problem is, what would you rather be exposed to? 1,000 rads of gamma rays or 1,000 rads of red photons? In other words, even though the amount of energy is the same, 1,000 joules of gamma radiation, will 1,000 joules of gamma radiation cause the same amount of damage as 1,000 joules of red photons? They're both 1,000 joules, right? But are they going to cause the same amount of damage? No, because we know that gamma radiation will cause a lot more damage. And so the rad isn't the best. The best, as far as radiation exposure, would be the sievert or the REM, right? And so what is REM? REM is this. REM is, they adjust it because 1,000 joules of red photons doesn't pack the same damage, the same punch as 1,000 joules of gamma radiation. They're going to weight those using the quality factor Q. And so if I take 1,000 rads here, you know, 1,000 joules per kilogram of matter, then we can see the quality factor here. And the quality factor is, the bigger the Q, the more damaging that radiation is. The smaller the Q, the less damaging. So if I look at the quality factor, Q is about 1 for X-rays. If Q is about 1 for X-rays, that means red photons must be way less than 1, right? Because red photons aren't going to cause any damage. What time do we go till? 40. So, okay, good. I want to finish this. But look at this. Is about 1 for X-rays and gamma rays. That means that X-rays, even though I'd rather be exposed to X-rays than gamma rays, X-rays and gamma rays have about the same punch according to this quality factor. They're going to cause the same kind of damage, right? Gamma rays should cause more, but it's still relatively small compared to, well, beta is the same. It's still comparatively small compared to neutrons. Slow neutrons cause more damage. And so if somebody's asking you, what would you rather be exposed to, you know, 1,000 rad of neutrons or 1,000 rad of gamma rays, what would you pick? I'd pick 1,000 rad of gamma rays. Because 1,000 rad of gamma rays should be less damaging. And 1,000 rad of gamma rays will have a lower REM or lower sievert than 1,000 rad of neutrons. Now, why are neutrons more damaging than gamma rays? You know, because if you need to protect yourself from X-rays, you just need a thin sheet of lead. If you need to protect yourself from gamma radiation, do you know what you use? No, not concrete. What's better is lead bricks. And so they make these bricks out of lead, and then you can build a wall of lead to protect yourself from gamma gamma radiation. Gamma radiation is much more penetrating than X radiation, right? But if you want to protect yourself from neutrons, how do you do that? Well, and why are neutrons so damaging? Because what happens is, if you stand in front of, let's say if you stand in front of gamma rays, is the gamma rays, will that necessarily make you radioactive? No, gamma rays cause chemical damage, right? Ions to form. But if you stand in front of neutrons, will that make you radioactive? Yes. It could make you radioactive. Why? Because, do you remember in the Rutherford gold foil experiment, the alpha particles, most of them passed through, but some of them were bounced back. Why were they bounced back? Because the alpha particle hit the nucleus of the gold. The nucleus of the gold atom is positive, the alpha particle is positive, you have huge electrical repulsions, it bounces back, right? But what if you shot neutrons? Would you ever see a neutron bounce back? No. Because neutrons have what charge? No charge. So there's no electrical repulsion preventing them from slamming into the nucleus. Now, these are slow, so these don't really have to slam very hard. But what happens is the neutron collides with the nucleus and gets stuck. If the neutron gets stuck with the nucleus, what's going to happen to the stability of that nucleus? It's going to go down, the stability. Or maybe it might go up. We've got to talk more about it. But as these neutrons start to stick to the nucleus, the nuclei are going to become less and less stable, and eventually they could become radioactive themselves. And so neutrons are quite dangerous. So we'll talk about this or finish this next time.